All right, so continuing with our logarithmic functions, we're going to talk about properties of logarithms. As you see, we got quite a few properties. First, we're going to start with product rule. We're going to let b, which is still going to be a base, and then we're going to have an m and an n are going to be positive numbers, and then b still can't be 1 because it's the base. So the log of base b of m times n is equal to the log of the base of m plus the log of the base, or log base b of m plus log base b of n. So the logarithm of a product is a sum of logarithms. And this has to go back to rules about exponents. So what we could say, according to these statements, like let's say we have log base b of m equals x and log base b of n equals y. Well, that means that m would just be b to the x, and then n would just be b to the y. So if I take a log base b of m n, well, that's just equal to the log of bx by, which is just going to be the log of, or sorry, log base b of bx by, which would be the log base b of bx plus y. And because it's the same base, we're just left with the x plus y. And back here, we know that x is just log base b of m, and y is log base b of n. So like I said, that comes from some properties that we know about exponentials, so we can change logs into exponentials and we can come up with this. So we're going to use the product rule to expand each logarithmic expression. So we got log base b of 7 times 11. So we can expand that. We're asked to expand. That means it's a log base 6 of 7 plus a log base b, base 6, sorry, we got 6, not a b, of 6 of 11. And that's all we need to expand. If I have log of 100x, well, we know that is 100 times x. So that is the log of 100 plus the log of x. And in this case, remember log is a base 10. So I actually know what power I have to put on 10 to get 100. That's going to be 2. So this is really just 2 plus log of x. So in these two cases, there's not a power that I can put on 6 that I know of that would give me that 7, or a power I can put on 6 that I know of they'll give me 11. I'd require a calculator. But if I was looking for exact values, I would keep it like this, and this would be the exact value here. So if we're able to simplify the logarithm into just a single digit without a calculator, then we'd like to try to do that. So quotient rule, same thing, a, b, and n are positive, b can't be 1. Here we have a product, so a quotient, log base b of m divided by n is log base b of m minus log base b of n. So the logarithm of a quotient is different, is the difference of the logarithms. So if we go back the same thing again, let's say x is going to be log base b of m, and y is log base b of n. And then we can say that m is just b to the x, and we can say that n is just b to the y. So if I do a log base b of m over n, well, that's just log base b of bx over by. And then because we got that difference here, that just turns into a log base b of b to the x minus y. That's how we get the subtraction, which leaves us with x minus y because we got the same base. And this is barely going to fit in here, so we know that x is just log base b of m minus y, which is log base b of n. So if we have something in the denominator, remember that is going to become subtraction. Things that are in the numerator, that becomes addition. So here we have log base 8 of 23 over x. If we were to expand that, we're going to have log base 8 of 23. Once again, I don't know a power of 8 that's going to give me 23, so we'll just leave it, minus log base 8 of x. Here we have natural log. So we have natural log of e to the 5th over 11, which is going to turn to natural log of e to the 5th minus natural log of y. And we know this one, since this is a base e log, so base e to the power of 5, let's just leave me with 5. So 5 minus natural log of 11. For our power rule, so here we're just going to have b and m, positive real numbers. B can't be 0. And then we're going to let p be any real number. So p doesn't have to be positive. It can be negative. The log base b of m to the power of p equals p log base b of m. So in this case, we like to really use this one to get rid of or move exponents out of the exponent position so we can play with them. All right, so sorry about that. So if we say that log base b of m is equal to some x, then we know that b to the x is going to be equal to m. So if we go back here and we go log base b of mp, that is going to be log base b, and m can be replaced with bx. We have bx raised to the power of p. So by properties of exponents, that just b turns in, so this multiplies, so we have b to the x times p. Then we have base b and base b, so we just left with the xp. So the p, we can't convert that to anything, but we know x is going to be log b of m. So actually, properties of logarithms get used a lot in calculus. So you're planning on taking calculus, this is going to be something you will use quite a bit. So we will use the power rule to expand each logarithmic expression. We have log base 6 of 3 to the 9. So according to our rules, what's going to happen here is this power gets pulled out here. So we're going to have 9 log base 6 of 3. So here, maybe you don't see a power right away, but remember, if I do a nth root, then I'm just raising to the power of 1 over n. So I'm doing a cube root. So this is natural log of x to the 1/3. Now we have an exponent. We can pull that out front. That is 1/3 natural log x. Here I got log of x plus 4 squared. So this is the only thing that we can pull out. That pulls out front. So we have 2 log of x plus 4. And we don't have a property to break up a summation or a difference, a similar difference inside of a logarithm. So there's nothing more I can do with this. I have to leave it as is. Our rules only apply to exponents, to products, and to quotients. All right, so these are just all your rules together. Like I said, m and n have to stay positive. So we know that if we have the log base b of m and n, then it turns into the summation of log base b of m plus log base b of n. If we have log base b of the quotient of m and n, that's just log base b of m minus log base b of n. And if we have log base b of m to the power of p, then the p gets pulled out front and we get p log base b of m. So we're going to start using these all together. So we'll do one example here. So we want to expand this expression as much as possible. So one of the things we notice is we got a quotient here. We got something on top and something on bottom. So I can use that quotient rule and go, well, this is just log base b of x to the 4th cubed root of y, and then minus the denominator, so log base b of 7. now we have a product here. So I can go, well, I can break that up further. I got a log base b of x to the fourth plus log base b of the cube root of y. And then we still have that minus log base b of 7. So I used the quotient rule because I had a quotient. Then I used the product rule so I could get at the product. And now what I can use the power rule. So let me write this one more time. This is log base b of x to the fourth plus log base b. So instead of saying the cube root of y, we're going to say y to the power of 1/3. And then we just have log base b of 7. So remember, 7 just has a power of 1 on it, so there's not much we can do. So if I use my power rule, that 4 comes out front, and we have 4 log base b of x plus 1/3 log base b of x minus just log base b of 7. I'll put a little tail on my log so we don't think they're ones here. So there are some places where being able to expand a logarithmic expression is going to be useful. And like one of the things one of the places I said was calculus and sometimes trying to solve certain problems. So there is a lot of benefit to these properties. So take a moment to have a natural log of x squared over 5y. And then you have log base a of x times y to the 6th divided by z squared times the third cubed root of 5. So take both of these and expand the expression as much as you can. Okay, so hopefully in a moment to work on that. So our quotient rule is going to be applied first. So we have natural log. So natural log we just treat like normal log. So natural log of x squared minus natural log of 5y. So remember, you got a minus here. So now when I use my product rule, the product only gets used on the second part. So what we have is we still keep that natural log of x squared, but we have this minus, and we have this product of 5 and y. So we do natural log of 5 plus natural log of y. But we had a negative out front of everything. So when this simplifies, we actually have natural log of x squared minus natural log of 5 minus natural log of y. So one of the things to notice here, in the previous example, anything was on top had a plus, and anything on the bottom has a minus. So we could have actually went from this step to this step by just going, oh, well, that's an x squared, so that's a plus. The 5 is on the bottom, so that's going to be a negative log of 5. The y is on the bottom, that's a negative log of y, which is actually how I'm going to do b here in a second. But now we have to do our power rule. So we have the power on the x, so we have 2 natural log of x minus natural log of 5 minus natural log of y, because we only have the one power. So b, like I said, I'm going to do a little cheat here. So if I look at what's inside my logarithm, x is on the top, so I'm going to have a log base a of x. Y is on the top, so that's going to stay positive, plus log base a of y to the 6th. Z squared is on the bottom, so we'll do minus log base b of z squared. And then that cubed root, so we know that, we'll write that as what it is, but we have 5 to the power of 1/3. That's on the bottom again, so we do minus log base, oh, a, not b. I got so used to the base b's, I kept making base b's. Base a of, we're just going to say 5 to the power of 1/3. So we know that's what it's going to become. So this took care of quotient and product rule altogether. So that's just another way to do it. You don't have to do it piece by piece. You can just look at it and go, oh, it's on the top, it's going to stay positive. It's on the bottom, it's going to stay negative or become negative. So now we have log base a of x plus 6 log base a of y, because we're using that power rule, minus log, oh, there's a 2 there, minus 2 log base a of z, and then we have that 1/3, so minus 1/3 log base a of 5. Okay, I am too far. There we go. So another thing that we want to do is sometimes we want to condense our logarithmic expression. So we know if we see something that's a log base b of m plus a log base b of n, that I can just combine that to log base b of m times n. If I have log base b of n, m minus log base b of n, I can combine that to log base b of m divided by n. And if I have p log base b of m, I can just combine that again, pull in the exponent, and now it's log base b of m to the p. So we're just taking everything backwards, and now we're condensing. So we want to write this as a single logarithm. So we have a plus here, so we know we have a product. And we have the same base log because they're both a base 10. Make sure you have that, because if you go back here, notice everything had the same base. So as long as we have the same base, I can go back to a base 10 log, and I would have 25 on top. Oops. That's right, the product. So we'd have 25 times 4. So in that case, 25 times 4 is just 100. So we have a common log of 100, which once again we know is 2. So that can be the benefit of it. It can combine with something that we can easily get a answer for. This one's not going to be as nice for us though. So here we have subtraction, so we know we're looking for a quotient. So we're going to have a quotient of what's inside the log. So we have a common log, and then this is going to be on top. We'll have 7x plus 6, and this will be on bottom. So log of 7x plus 6 minus log of x just turns into log of 7x plus 6 divided by x. Okay. So we hadn't done a product, but we have one in here for you to try on your own. So we have 3 log x minus 6 log y. So combine that into a single log. And then you have a natural log of 2 plus 13 natural log of a minus 1/2 natural log of b. So try your best to combine that into a single log. And if you end up with fractional exponents, try to convert them back into radicals. So anything that appears on the outside of that log is going to turn into an exponent. So we know that this 3 is supposed to go back in here and become a log of exponent of this x. So we know that we have log of x cubed, and the 6 goes back in this y, minus log of y to the 6th. We also see that we have a difference, so we know that we're going to have a quotient. So we're going to have a quotient. So whatever's positive stays on top, so the x cubed stays on here. This is subtraction, so then the y to the 6 goes on the bottom. Here we got natural log, so we know this is an exponent and this is an exponent, but everything still works the same even if it's natural logs. So we have natural log of 2 plus, so 13 goes back inside, and that becomes natural log of a to the 13. And then this 1/2 goes back into a natural log of b to the 1/2. So we know this property, if I have the nth root of a, then I have a to the 1 over nth power. So if we go backwards, we got a 2 here, 1/2, so we know we're going back to a square root. So this is just log of 2 plus, natural log of 2, natural log of a to the 13 minus natural log of the square root of b. Now anything that's plus is going to be your product. And anything that's a minus goes into your quotient. So it tells you if it's going to be in the top or the bottom. So natural log, so this is a plus out here, right? This is a positive, this is a positive. So the 2 and the a to the 13 go on top. This is a negative, so then that square root of b goes on the bottom. Let me just write that one more time so it looks a little cleaner. So you have 2a to the 13 divided by the square root of b. So I accidentally wrote a earlier. Change of base formula. This is used a lot of times for calculators. So most of your calculators, unless you have a special one, will do a common log and it will do a natural log. If you have any kind of other base, it will not be able to do that unless you use this formula. So for any logarithmic basis of a and b and any positive number m, log base b of m will be equal to the log base a of m to log base a of b. So if I'm in base b, but I want to change to base a, all I have to do is just put the m up here and put the b down here. That means if I had a log base 3 of x, and I wanted to write that as a common log, so I'll put the base 10 here just for now. But if I want that common log, so we change this base, then the x is going to go up here and the 3 is going to go down here. So since your calculator can handle a common log, I could actually look at a log base 3 with my calculator now. So it's the demonstration right here. This is going to be 3 to the. So what I want to graph is I want to see what the inverse would look like. So y is log base 3 of x. So one of the things we know, just to prove that we actually find the inverse here, that 3 of x goes to the point 0, 1 and 1, 3. Therefore, its inverse just goes to the points 1, 0 and 3, 1. So if we want to get this, which was the one we already just did, said that all I need to do was just the natural log of x and then divide by the natural log of 3. We keep that base. And as you see, we do get that inverse function. So that is how I can graph y equals log base 3 of x. Is I have to use that change of base formula. So I already introduced with a common log, but essentially if I have any base, I can model it with common logs by just taking log base b of m and just doing log of m divided by log of b. If I was wanting to convert into natural logs, I can do log base b of m, and I can convert it into, or change it to base e log, is do natural log of m divided by natural log of b. Always remember, it's your old base goes in the bottom. So we're going to put this in a calculator in a bit. So let me just make a little spot to the side to put our information in. So we want to use a common log to evaluate log base 7 of 2,506. So if we try to convert this to, say, we're going to use common logs. So remember, the old base goes on the bottom, and then what's in here, this number goes on the top. So we're going to bring up your TI-84 here in just a second. So now, like I said, as you see, we just have common log and natural log. So we just hit log 2,506, and then we divide by log of 7. And what we get back is 4.0219965154. So if this is correct, that means if I take 7 and I raise it to the power of 4.0219965154, we should expect to get 2,506 back. So let's just see. 7 raised to the power of 4.01, oh, sorry, 0.219965154. And as you see, we get 2,506 back. So yes, we did actually find we found a log base 7 of 2,506. So that exponent you have to put on 7 would have to be that 4,000, or maybe that 4.0219965154. More than likely, you'll have to round these answers. You will not see this looking exactly the same. Like, let's say I had to round to that. You can still kind of get some proof that you actually found the right answer. It's just, in this case, it's really, really close to my answer, just a little off. So that's one of the problems we have with exponents. I only have to lose a couple decimals and it starts getting me things that, you see, there's quite a bit of difference there. But still, it's kind of close. Just bear that in mind. If you want to check if your answers work, you're going to have to put in quite a few decimals to get there. If I add one more decimal, then you see we're really close. So here we got, we want to use natural logs to evaluate the same problem. So we should know what the answer should be. So we should be getting the same answer back. So in this case, we would just take log base 7 of 2,506, and all I'd have to do is natural log of 2,506 divided by the natural log of the old base, which was 7. So bring up my TI-84. So remember, here is natural log. So I hit natural log of 2,506, and then I close parentheses, divide by natural log of 7, close parentheses. I hit enter, and we see we get the same answer back. We get 4.0219965154. Try on your own. Use a common log to evaluate log base 4 of 7, and then use a natural log to evaluate log base 0.75 of 0.421875. Okay, we got log base 7 of 4, or sorry, log base 4 of 7. So we would just, if you convert to a common log, that's log of the 7, and then remember the base goes in the bottom, so log of 4. Log of 7 divided by log of 4. We get 1.403677461. Now for log base 0.75, or log of 3/4, a log base 3/4 of 0.421875. We're going to do natural logs for that one. So we'll do a natural log of the 0.421875 divided by the natural log of 0.75. So there's really not a big reason currently to choose a common log over a natural log or a natural log over a common log. That's to deal with other problems later. But if you're just trying to do, like, you have a base 4 log and you just want to figure out what it is, you can use either common or natural logs. It's not going to matter. If we do natural log of 0.421875 divided by natural log of 0.75, we're going to get 3. So remember, this means that if I take 7 and I put the power of 1.403677461 on it, I should get 7 back. And this is telling me that if I take 0.75 and I raise it to the power of 3, I should get 0.421875.